based invariants of manifolds via algebraic theory. And this is a joint work with Hoekzema, Murray, Merlin, and Roy. Mm. And it all started as a women in topology um, project. But then we continued in different groups. So I will just tell about our joint project today. And in the end, I will tell about continuation. So the plan will be to talk about a classical story first. So it's a 200 years old story about Caesar's congruences for polyhedra. Then I will define what are SKN groups for manifolds that will be quite analogous to these classical groups. Then we will continue with the so-called K-theory with squares. That is a generalization of the algebraic K-theory construction, for example, of Waldhausen. But this is something that is more modern and can be applied in more various situations. And finally, I will tell you how to apply this machinery to construct some interesting spectrum that recovers this cut and paste group of manifolds. And so let's start with a very classical story. The Caesar's congruences in classical setting. So let's look at polygons in R2 just on the plane, and we will call two polygons in R2 are called Caesar congruent. So this is Caesar's congruent. So if and only if, and let's call polygons P and Q. So they are Caesar congruent if we can decompose them into congruent pieces. So Qi and Pi are also polygons. We say that we allow those intersections of Pi and Pj only on the boundary, so measure of this is 0. The same for Q. And Pi should be congruent to Qi. So example, let's start with a rectangle. So we can cut it like this, and then it is, so this is our P. Then we rearrange these pieces, and we get a triangle. This is Q, and these are Caesar congruent. No one told that this should be convex or connected, so this is also congruent just to disjoint union of two triangles. More examples, something like this. So this is congruent to, and then we pass this triangle. So these are all examples of Caesar congruent polygons. And well, it is obvious that if two polygons are Caesar congruent, then they have the same area. And this is if and only if statement. So this is very famous theorem from Bolyai, proved more than 200 years ago, that two polygons are Caesar congruent if and only if they have the same area. So next, after 100 years after this theorem, Hilbert Hilbert presented in his list of problems on the congruence. Um, Problem number 3 was the question: is volume enough to detect the same thing in R3? So if you have two polyhedra in R3, and now your Caesar congruence is you cut along planes, and you decompose your polyhedra into disjoint, not disjoint, into union of other polyhedra, and you allow to move this polyhedra and compose a new one. So is volume the only invariant? So is volume enough to detect Caesar congruence for polyhedra? Um, and the answer is no. And it was shown by Dan that if you take a tetrahedron of volume 1 and if you take a cube of volume 1, they are not Caesar congruent. And what distinguishes them is something that is called Dan invariant, so they are not Caesar congruent. And there is Dan invariant such that tetrahedron has, sorry, Dan invariant of tetrahedron is non-zero, so let's say 1. And then invariant of a cube is 0. And then invariant is something very easy. So if you have a polyhedron, you just write a sum, where sum runs over all edges, and one takes length of the edge and the dihedral angle at this edge. And this is something that lives in the tensor product of R and R mod that pi. And it is obvious that for cube it's 0, for tetrahedron one can show it's not 0. And next the question is, okay, we have now volume and we have this Dan invariant, so is this enough? And the answer is yes. So this is a theorem of theorem by Sidler that says that these two invariants, volume and Dan invariant, are enough to characterize the Caesar congruence in R3. So yeah, what's next? We can go also higher. So you can ask all the same question in Rn. And also you look at polytopes in Rn. You can define what is Caesar congruence the same way. And also there are analogs of Dan invariant, of the Dan invariant. So this is now not one invariant, this is a bunch of invariants. And they are called Dan invariants. And the question is volume and this set of Dan invariants enough to characterize Caesar congruence in Rn? And so for R4, the answer is yes. So there is an analogous theorem to Sidler's theorem in R4, but for Rn greater than 4, it is O. So it's not clear whether this set of invariants is enough. And also you can do this, but not working in Rn, but in hyperbolic or spherical spaces. Analogous question of hyperbolic spherical setting. also still open. But we can go even further and and ask what about groups? So what about Caesar congruence group? So what is this? So far I will work only in Rn. So Caesar congruence group in Rn is defined by generators and relations. So it is generated, so it's a abelian group generated by set of all polytopes in Rn. And we quotient out the Caesar congruence relation. So if we have two polytopes that are Caesar congruent, then we quotient out this. And we say that sum in this group is just given by disjoint unit. But we also quotient out this relation. And we call this Caesar congruence group. And the question is, what is this group? And maybe, so it might seem, for example, easy in R3, but actually it's even in R3 it's not so easy. So I told you that volume and then invariant. So volume it's R, so volume can live in R. Then invariant can live in the tensor product, and you might say, okay, it seems like it's just direct sum of those two invariants, but it's not. So if you just write the sequence like this, so we work in R3. This map that takes any number in R to the cube of the corresponding area. Okay, R plus, not R. And then if you take a then invariant that lives in this tensor product, then actually this is not an exact sequence. There is something also here. So I don't want to tell what is this, but the message here is that this group is not so easy. It's not just these two invariants. It has more structure. And I just want to write such a sequence for hyperbolic case, also for H3, just to motivate a bit why K-series is a natural thing to appear here. So now it's sorry. Now it's a Caesar congruence group in hyperbolic space, three-dimensional. We also have then invariant. And here as a co-kernel, we have K2 of complex numbers. So this minus, maybe I don't explain what it is. So it's not exactly K2 of complex numbers. It's a certain eigenspace, -1 eigenspace of complex conjugation after rationalization, but that's not important for this talk. I just wanted to show that even when you study these classical groups and you try to write these exact sequences involving then invariant and volume, you see that K-series already appears as a co-kernel. And what is a modern approach? So as I told you, even it's not known that then invariant and volume are the only invariants. So it's not hard to expect that, not unusual that these groups are not known. So what are those scans? So this is also open in some sense. What do I mean by open? So there are such sequences um, are also known for higher degrees, for higher dimensions. So not only for R3 or H3. And this, in some sense, is answer what are these groups. But I even think that for higher dimensions, some of them are like open questions. What are the sequences? And this is due to Goncharov. So what Campbell and Zakharevich, they suggested that it might be useful to introduce certain machinery. So these are called assemblers. This is due to Zakharevich and subtractive categories. And these are certain constructions out of which you can construct a spectrum. Sorry. That recovers this classical Caesar congruence group as pi naught of this spectrum. And this spectra contains certain interesting information in higher homotopy groups. So idea is to construct a spectrum in some natural way that recovers the Caesar congruence groups as a pi zero of the spectrum. And hope spectrum, hope that it contains some interesting information in fibers, which is the case. So that's the setup that more or less we will be inspired by in the next part of the talk. So of course I didn't tell you what are those assemblers and subtractive categories, and we are not going to use exactly this machinery. Historically, this was what was happening first. So exactly this construction, they are independent. So these two people just came up with this two independent approaches, and they in the end obtain the same spectrum. So that was a natural thing to do. And so what we want to do is to apply this machinery that they applied to classical Caesar congruence group. We want to do almost the same thing, but for the so-called Caesar congruence groups of manifolds, and they're called cut and paste, but basically these are synonyms. And now we are coming to the part where I will define to you what are these SKN groups. So part 2, SKN groups, and this is what we are going to study using this machinery, and not exactly to study the groups, but we will construct in the end a spectrum that S pi naught has these SKN groups. We will use the machinery of Campbell and Zakharevich, and this will be some natural and interesting spectrum to discover. So what are SKN groups? So we fix the dimension, so n is just a number that is fixed, and we say that two manifolds that are n-dimensional, so n n-dimensional, smooth, closed, oriented manifolds. We call them SK equivalent. So actually what is SK? So S and K stands for Schneiden und Kleben. And that's because people who first studied these groups, they were from Germany. So Schneiden is cut, Kleben is paste. Um, so they are SK equivalent if we can write M as a union of two submanifolds glued along some diffeomorphism and N the same, two pieces, but glued along another diffeomorphism. So picture. So let's say that this is our M1. So I never said that M1 and M2 should be connected. They don't have to be. So this is my M2. And if I glue them like this, so this is my phi, then I will just get surface of genus 2 and the sphere. So this is my M, but I can glue them in a different way, like this. This is my psi, and then what I will get, I will just get 2 tori. This is my N. And by definition, they are SKN equivalent. So in other words, what you do, you take your manifold, let's say M, and you cut it along n minus one dimensional manifold. And after this cut, you allow to rearrange the pieces along another diffeomorphism. And this is what it means to be SKN equivalent. Or in more formal way, it is what I wrote with M and N and phi and psi. So okay, now we have this analog of Caesar congruence for manifolds, and we also analogously as before, as previous, we define SKM groups. So SKM is just a Grothendieck group of monoid of these manifolds of all n-dimensional smooth oriented manifolds under the disjoint union and modulo this SKN relation. So it's just exactly the same as before, but in different words. So if you want it in terms of generators and relations, and you take all n-dimensional manifolds, and you quotient out that sum of two manifolds is just disjoint union, and you quotient out this SKN relation. But actually, these groups, on the contrast to classical Caesar congruence groups, these groups are easy. And so let's see just a small example. What is SK1? So all one-dimensional manifolds that are closed, these are a bunch of circles. And what we can do with a circle, we can cut it like this. So let's make cut at this purple points. and black is my M1. This turquoise color is my M2. And I can glue these two pieces in a different way. So I can glue not like on this picture, but these two pieces together and these two pieces together. And this will mean that I will have a picture like this. And circle is SK1 equivalent to the joint union of two circles. So class of the, so S1 is just 0. So it looks like the tautology, but it's something meaningful. So SK1 as a group, it's trivial. It's a trivial group. And actually all SKN, they are not trivial, but they are null. And so if n is odd, then they are trivial, as we saw for SK1. It is z plus z if n is 0 mod 4, and basis is given by Sn and projective space. So n is divisible by 4, and it is just z for n is 2 mod 4. And as you might guess, the only, from this formula, the only invariants are Euler characteristic and signature. So these are the only SKN invariants. And combination of these two. So yeah. But still, so it is interesting just in terms of what kind of spectrum will we get if we try to apply the same machinery as Zakharevich and Campbell did for classical seesaw congruence group. So we still do that, but now we will need a small modification of this definition. So these SKN groups, they are also something very classical that was considered maybe not 100 years ago, but like 50 years ago. But they are not good enough for this machinery, and I will explain why. So imagine that you want to do a construction like a K-theoretic construction, and you start with some category. And all the objects of the category, they should be of the same nature, so to speak. So if you just want to construct K of Z, then these are projective modules over Z, so abelian groups, finitely generated. And in this case, we want a category that will encode this cut and paste relation for manifolds. But when you start with a closed manifolds, and you cut it, then these pieces that give you these relations for cut and paste group, they now have boundary. So if you want the category, this can't be a category of just closed manifolds, because to encode some relations, you suddenly need objects of a different kind. So now I will have to introduce alternative groups that are somehow like SKN groups, but that will use all the objects of this category, and our category is manifolds with boundary. So alternative definition prime. So we defined previously what is SKN. So it was Grothendieck group of monoid of n-dimensional smooth closed manifold here, closed. And I will do all the same. So SKN delta. And I will define it just exactly the same. So this sign partly I realized that not everyone knows what is this sign. So this sign means all the same that was above. But now we are using not closed manifolds, but manifolds with boundary. So we take a Grothendieck group of humanoid of n-dimensional, smooth, oriented, compact manifold that might have boundary. And what it means to be SKN equivalent if you have boundary. It's also all the same. So you take two M and N and they are equivalent. If you can do the cut and your cut is not allowed to touch the boundary. So your cuts should be nice. And then it's it's just the same definition. So you say, okay, I start with some manifold, I cut it along codimension one some manifold, it decomposes into two pieces, and then I allow to glue these two pieces back by different diffeomorphism, and then I get another manifold, and this will be SKN boundary equivalent. So just a picture of this definition. So let's say we started with a manifold like this. And where can we get? So for example, we can make cut here and cut here. And so swap in some sense these two lower pieces, and we will get a new one that will look like a torus. And a cylinder. And this is where our cuts were. And these two guys are SKM boundary equivalent. So okay, now we have groups that you want to work with. Now they are, so we have generators, and they are also from the same category that encoding pieces for the relation. And small lemma. Oh yeah, sorry. So how these groups that are new SKN boundary, how they are related to old groups SKN that are classical. And actually they just fit into an easy exact sequence. So SKN, these are previously defined group, SKN boundaries, these are newly defined group, and CN minus one is a subgroup of Grothendieck group on all n-dimensional, n minus one dimensional manifolds generated. So for me, manifold is always oriented, compact, smooth. So this is subgroup of Grothendieck group of n minus one dimensional manifold generated by manifolds cobordant to empty one. Cobordant to zero. And so this is not a hard, but also it's not obvious thing to show that this subgroup is a free abelian group. So this is a huge free abelian group. And so it means that this SKN with boundary is just a direct sum of this old group and this huge free abelian group of manifolds that are cobordant to zero. So now it is time to introduce what is case theory with squares. So I remind you what was the goal. The goal was to construct in some meaningful way some spectrum that will recover these SK groups of manifolds as it's pi zero. Yes, and hope it is a nice, interesting spectrum. So for this, I will need this machinery that is called K-square theory. So in the beginning, I told you such words as assemblers and subtractive categories. So these were pre relatives of this K-square theory that were applied to those specific purposes of classical Caesar congruence groups. But so we just looked at those constructions and they just don't work in our case. So some conditions that they needed for certain categories to be fulfilled, they just fail for manifolds. But we were extremely lucky because they just generalized all this. Those constructions were quite nasty, and Campbell and Zaharevi, they generalized it to this new construction of K-square theory, and this works. This just is applicable to the case of manifolds. So I will tell you what kind of setup we need for this square case theory and what is a construction. So I will define you what kind of category first. So it will be something that is called category with squares and the category with squares. So it is a category, C. Equipped with a choice of two families of morphisms. So it was choice of two subcategories of morphisms. And we will call them and denote them like this. So this will be cofibrations. And like this for fiber mesh. So these are just names. This is how they decided to call them because they were inspired by Waldhausen notations. So these are just two subcategories, nothing complicated. And notion of squares and distinguished squares. So how squares look, this is just a diagram where vertically you allow one type of errors and horizontally you allow another type of errors. And you require that this is a commutative diagram in our category. So both of them are morphisms, so you can compose them and you require that squares are commutative. And we don't say that any diagram like this can be called a square. So in normal language, of course, it is a square, but we call them distinguished only if they live in this chosen family. And family is the one that we choose. And it has to satisfy certain properties. And properties are as follows. So far, what we have category, we have two subcategories of morphisms and notion of squares. So what are conditions? And conditions are basically, so I will list the conditions and then I will explain how you remember it very easily. So first one is both of these subcategories of cofibrations and cofiber maps, they should contain isomorphisms. So they are forced to contain isomorphisms. All isos. Second condition, So squares commute, this is what I told you, but I did not write it. So squares commute and compose horizontally and vertically. So what it means, if you take two squares with a common side and you stack them together, so you can write a new diagram, and this new diagram is forced to be a distinguished square. So it is, of course, a square, but it has to live in this chosen family. And also some condition on the category, so it has to have coproducts and coproduct of two squares is also a square. So squares are closed under coproduct. And one more technical condition, but so what it all means? It just means that if you want to consider a bisimplicial set given by these squares, so what it means that if I say that squares of size ij, so if I write it like this, if I write a rectangle of size ij, so I here, j here, and every square here is a square, uh, a distinguished square, then I just want to force my definition to allow me to consider a bisimplicial set given by set of ij squares. So for this, I need squares to compose such that I can consider this big square composed out of small ones. I want to be able to delete one row or one column or to add identities. So this is a bisimplicial set. So this is basically what this definition is trying to do. It says that if I have some notion of those squares, I should be able to consider a bisimplicial set given by this kind of definition. So now I explained you what is a category with squares, and now a construction. So given C square, so category with squares, this is my notation. We can consider this bisimplicial set where ij simplex is given by I times j square like this. And sorry. So this is my set of j simplices. And every square, every small square in this diagram should be distinguished square from the definition. So I can define this. And then what I take, I define a space given by geometric realization of this bisimplicial set. And it turns out to be an infinite loop space. And I will denote it like this, because in some sense I'm just taking a nerve of a certain simplicial category. So, and this nerve is a bisimplicial set. So this is my infinite loop space, and I define k square of this c square to be loops of this geometric realization. So I would like to loop once more. And this is a construction. So this is how you define this spectrum that comes from the category with squares. And so now the natural question would be, why is it actually called K-series? So how does it generalize other K-series, classical ones? And here the answer is very nice and natural. So if we start with C, Waldhausen category, then what can we do? We can turn it, just given all the data that comes with the notion of being Waldhausen, we can make it into the category with squares. So we can associate this notion of distinguished square. And this becomes a category with squares. And how do we do it? So we define the distinguished squares in this category as those that look like this. So in Waldhausen category, we have a notion of cofibrations. So these are cofibrations. So we look at all commutative squares where horizontal maps are cofibrations, and we require that D is weakly equivalent to the push out, like this. So we know that in Waldhausen categories, push outs along cofibrations exist. So we can take a push out of this part, and there is this map from universal property, and we require that it is a weak equivalence, and weak equivalence is also something that is coming from the Waldhausen category data. So if we do this, if we start with Waldhausen category, we turn it into category with squares like this, then the classical construction of Waldhausen gives the same spectrum, so equivalent spectrum, as this construction as I just described it to you, applied to this category of squares from this definition. So this is why this construction is a generalization of the Waldhausen's construction. And so a theorem due to the Harevich and Campbell so they tell us how to compute K0 of such a category. And this is very easy. So this is just a group, again, given by generators and relations. and generators are just all objects of C, and the relations are those coming from squares. So this is what is known, and now we are going to apply this machinery and this theorem to construct a spectrum out of manifolds. So this is the last part. So it's SKN groups via K-square theorem. And for this, we need a category with squares. And now I will define for you, so what is a category and what are squares in this category? And what are these two subcategories of morphisms? So category is very natural. So this is just manifolds with boundary. So this is category of smooth, compact, oriented, n-dimensional of I will omit all these objectives. So of n-dimensional methods with boundary. Of course, boundary can be empty, but I just want to emphasize that we allow boundary. And maps are just smooth maps. Sorry, morphisms are smooth maps. And now I need to define what are these two subcategories of cofibrations and cofiber maps. So this and this, they are both defined to be, those have to be smooth embeddings. Such that boundary is sent either entirely to the interior or to the boundary. And it has to have a trivial normal band. So what it all just means? It means that if you have an embedding, what is allowed? So it is allowed that it goes like this. So this is fine. So this cylinder just goes to this part. Also, it would be fine if this cylinder entirely goes to the interior. So this is also allowed. What is not allowed, so this is fine. And what is not allowed is to have something like this, that boundary goes partially to the boundary and then goes to the interior. So this would not be allowed. So this is no. So basically our maps are just some nice maps such that if you cut along the boundaries at the left, you can decompose it into two nice manifolds. So these are smooth embeddings that are these two subcategories. And what are squares? So I just define what are squares, and squares are push out. What does it mean to be a push out? It means to be a push out in the category of spaces. So squares are commutative squares that are push outs in top. So it means that if I look at some commutative square, gluing result has to be manifold again. And gluing means in the sense of in the topological sense. So example of such a square would be, for example, like this. So include cylinders as collars of the boundary. Maybe it's a bit confusing that this arrow looks like it has to be surjective, but this is just a notation. And the gluing result is this. So this is an example of distinguished square. And now we are good to go. So this is now a category with squares, and I only have to apply this construction. So um, so this is a theorem due to my co-authors and me. um, so manifold with boundary is a category with squares. So all those requirements that are asked from this category are fulfilled. And if you compute pi naught of this spectrum that we construct using this machinery, then what we will get, so when I write k naught, it just means pi naught of this spectrum. Then it is sk and this boundary, so exactly those groups that we wanted. But then we can go further. So if we look at the category of manifolds with boundary, and we look at the category of homologically bounded chain complexes over Z. So it means that homologically bounded means that if I have a chain complex, it is equivalent to one that has all the groups concentrated in finitely many degrees, and they are all finitely generated over Z. So if I start with a manifold and I send it to its singular chain complex, so since my manifold are compact, I will get a chain complex that is not just arbitrary, but homologically bounded. Then such a map of categories induces a map of spectra. And so on the left-hand side, it will be this k-square spectrum of manifold. And on the left-hand side, it will be k-square spectrum of chain complexes. But as I told you, if we have a Waldhausen category, then it is the same as Waldhausen's construction. So we can just remove this square. So then it will be Waldhausen K-theory of chain complexes homologically bounded. And in turn, it is well known that you can forget that these are chain complexes. This is just K of Z. So we have a map from square K-theory of manifolds to the usual K-theory of integers. And if we look at K naught of this, so K naught of squares, so by part one, we know that this is skn delta. and it should go to pi naught of k of z, and this is just z, integers. And what is this map? This map is actually a very natural map, which sends, so in skn delta, you know that every element is represented by a manifold, and it sends a class of the manifold to its Euler characteristic. So this is second part of the theorem. So not only we constructed the spectrum, but we connected it to k of z, and we lifted this Euler characteristic as a map of spectra. And just one more minute to finish. So as I told you in the beginning, invariance, skn invariance, Euler characteristic and signature. So work in progress is to lift the signature. So part 2 lifts Euler characteristic, and we want still to lift the signature as a map from k squares manifolds to L spectrum of Z. And also, if you unravel all those definitions and construction of this case theory of manifolds, then it looks very much like MTSON in the following sense, that if you look at loops of cobordism category of the space, like space, infinite loop space that is B corp n, you take one more loop space, this is MTSON. And if you take edgewise a subdivision of this, it is almost like our construction, but with little differences. And work in progress here is to say whether actually our construction is different from B corp n and how they are related. I think one is either a subspace of another, so they are very closely related. But it's like we still have some difficulties there. And that's the end. Thank you.
Higher version like cubes and so on, like getting higher multisimplicial sets.
Can somebody repeat the question for me?
Is there a notion of categories with distinguished cubes?
Wow, that's a very good question. So, yes, and this is what we came up. So I think Zakharevich and Campbell, they thought about this, but they never wrote it down. Like they didn't need this version, but to do this part, so lift the signature. So we can't really so far leave the signature, but we could categorify some other groups that are coming in between, like here, like this. So we think it should go like this. And here there is something that is called SK bar. So this is something like SK groups, but with more relations. And these relations are coming from cobordisms. And we can categorify this group. So we categorified this by categorified, I mean, we constructed a spectrum that has pi naught this group. And to construct this spectrum, we exactly use cube case theory. So yes, the answer is yes, and we even used it.
Okay, thank you.
All right, if not, we thank Julia again.